Cruise Performance Chart. So far, we have charts for predicting takeoff distance, landing distance, and time and fuel to climb. Now, let's look at a chart to help compute en route fuel consumption and expected true airspeed. This chart is the Cruise Power Setting chart, shown in Figure 25. Once again, Machado's Fire and Brimstone chart principle number 666 says, "Always read the notes before using the chart, lest you be visited by perdition's dark and evil forces." The note at the top of the chart assumes the engine operates at 65% maximum continuous power or full throttle. Remember, at higher altitudes, even though you have full throttle applied, you might not be able to develop 65% power. The 65% power figure is based on the RPM and manifold pressure settings provided in the chart. Obviously, this chart is for an aeroplane with a constant speed propeller, since it has both manifold pressure for power and RPM column for prop speed. 3 temperature sections exist on the chart. The middle column is for standard temperature, or ISA. The left and right columns are sections for temperatures below and above standard conditions, respectively. Within each section is an individual temperature column, listed under IOAT, indicated outside air temperature, for variable temperature conditions en route. When you are given a pressure altitude and temperature, simply find the pressure altitude on the far left column and proceed to the right until you are near a temperature similar to that for your cruise altitude. If it's not exact, that's okay. Just get as close as you can. Immediately to the right will be the RPM and manifold pressure settings required to develop 65% power with the associated fuel flow and true airspeed for those settings. Cruise Performance Problem Number 1. Using Figure 25, approximately what fuel consumption and true airspeed should you expect for a flight under the following conditions? Pressure altitude 8,000 feet. Temperature plus 22 degrees C. Manifold pressure 20.8 inches of mercury. Wind calm. Find the 8,000-foot pressure altitude line and follow it horizontally across until reaching a temperature of or near plus 22 degrees C. This puts you in section number 3 of the charts, or in the higher than standard temperature section. To produce 65% power on an engine RPM of 2,450 and a manifold pressure of 20.8 inches of mercury are necessary. Under these conditions, you can expect a fuel flow of 11.5 gallons per hour and an estimated true airspeed of 164 knots. Cruise Performance Problem Number 2. Using Figure 25, determine the approximate manifold pressure setting with 2,450 RPM to achieve 65% maximum continuous power at 6,500 feet pressure altitude with a temperature of 36 degrees Fahrenheit higher than standard.
A temperature of 36 degrees Fahrenheit higher than standard would put you in section number 3 of the chart. The temperature of ISA plus 20 degrees Celsius is 36 degrees Fahrenheit above standard temperature. If we follow the 6,000-foot pressure altitude value to the third section, we find a manifold pressure value of 21.0 inches. Since 6,500 feet is slightly higher than this, let's interpolate. The 8,000-foot pressure altitude line shows a manifold pressure of 20.8 inches. We can assume that at 7,000 feet, the manifold pressure required is 20.9 inches. The value we want is halfway between 6,000 feet and 7,000 feet, or halfway between 21.0 and 20.9 inches. So, 20.95 inches is the manifold pressure required at 2,450 RPM to maintain 65% power. Realistically, you'll use 21.0 inches of manifold pressure since your power gauges and your eyes aren't calibrated to read in the hundredths. I suppose you could use a small magnifying glass, but under the wrong sunlight conditions, you might burn a little hole in the instrument. Just kidding.
Cruise performance problem number 3. What fuel flow should a pilot expect at a pressure altitude of 11,000 feet on a standard day with 65% maximum continuous power using Figure 25? Standard day ISA conditions are found in section number 2 of the chart. Since there is no value for 1,000 feet, locate fuel flow values for 10,000 feet and 12,000 feet. The fuel flow for 11,000 feet will be halfway between these values. Simple interpolation. 10,000 foot fuel flow value, 11.5 gallons per hour. 12,000 foot fuel flow value, 10.9 gallons per hour. 11.5 plus 10.9 divided by 2 equals 11.2 gallons per hour for 11,000 feet.
It's hard to believe that people can run out of fuel in airplanes. The fact is, they do. That's why Machado's above-the-ground fuel rule says pilots coming close to running out of fuel in an airplane can get a $200 advance from an undertaker anytime they desire.
Another variety of cruise performance charts. A different variety of cruise performance chart is shown in Figure 26. This chart is for an airplane with a fixed-pitch propeller. Pressure altitudes are found on the left side of the chart, with variable RPM settings for variable power conditions. Unlike our previous chart, this chart allows us to choose various percentage selections of BHP, brake horsepower, with which to operate. In other words, if the aeroplane has a 100 horsepower engine, this chart shows what percentage of those 100 horses are being used. Similar to the chart in Figure 25, this chart has 3 temperature columns. Let's try a few problems. Cruise performance problem number 4. Determine the expected fuel consumption and true airspeed for a flight at a pressure altitude of 4,000 feet at 2,300 RPM under standard conditions using Figure 26. Find the 4,000 foot pressure altitude column, then move to the 2,300 RPM value. Directly across is our expected true airspeed of 95 knots and fuel consumption of 5.1 gallons per hour at an expected power output of 63%. Are you wondering why we want to know how much power our engine is producing? In many aeroplanes, leaning of the mixture is recommended when the engine is producing less than 75% power. This chart lets you know when it's reasonable to lean the mixture for more efficient engine operations. It also provides information that might be required in computing values based on other performance charts. Since this chart doesn't have detailed calibrations for various temperatures, what do you do if the temperature is only slightly different from the values listed in one of the 3 vertical temperature columns? The answer is to pick the temperature column closest to the actual air temperature. Cruise performance problem number 5. Using Figure 26, determine the expected fuel consumption for a flight at a pressure altitude of 5,500 feet at 2,400 RPM under conditions 14 degrees C colder than standard for your flight altitude. We'll use the first temperature column since 14 degrees C colder than standard is closest to its minus 20 degrees C below standard value. Notice that we're using 5,500 feet, which isn't shown on the chart. A little interpolation is necessary here. Fuel flow for 6,000 feet at 2,400 RPM is 5.8 gallons per hour. Fuel flow for 4,000 feet at 2,400 RPM, 6.1 gallons per hour. From this, you can find the fuel flow for 5,000 feet. 5.8 plus 6.1 divided by 2 equals 5.95 gallons per hour at 5,000 feet for 2,400 RPM. Now, find the fuel flow for 5,500 feet at 2,400 RPM. This is the difference between the 5,000 foot and 6,000 foot values. 5.95 plus 5.8 divided by 2 equals 5.87, or approximately 5.9 gallons per hour. Let's be practical about this. Looking at the numbers, you can usually eyeball the correct value without much difficulty, even without interpolating. This is made much easier when chart values don't vary much between conditions. In other words, at 4,000 feet in this example, we had a fuel flow of 6.1 gallons per hour, and at 6,000 feet, we had 5.8 gallons per hour. It's fairly easy to see that the value for 5,500 feet is closest to 5.8 gallons per hour. In the real world, this works fine. For FAA testing purposes, you want to be as precise as possible. There is nothing wrong with taking liberties at estimating values as long as you know how to be precise when the need arises. Endurance and range profile charts. Figure 27 and 28 are two additional charts you might see. Figure 27 is a best endurance chart and Figure 28 is a best range chart. There are many times when knowing your endurance and range is of immense value. For instance, if I had to remain airborne until the weather cleared for landing, the endurance chart would be of immense value. I'd know how long I could afford to hang around while flying in circles before heading to another airport. To use either chart, you need to know the percentage of power developed by the engine. Given that information, you can find your endurance and range for various altitudes. Just where will you find the engine's power output in percentages? From the typical cruise performance charts we've already seen in figures 25 and 26. If we were using 65% power, what would our endurance be at 8,000 feet? Simply find 8,000 feet in figure 27 and move across to the 65% power line. Drop straight down and find an endurance of 3 hours and 36 minutes. 5 divisions between our marks equals 12 minutes per division. At 65% power, according to figure 28, our range is approximately 354 nautical miles. Of course, assuming you've read all the conditions in both charts, you'll know the range is based on no wind, and both charts yield numbers which include a 45-minute fuel reserve. Crosswind component chart. The only pilots who don't have to worry about crosswinds are aircraft carrier pilots. They have a lot more to worry about than crosswinds. Their runway is always moving. How would you like to take off, then return to find your airport has moved to another location? And I bet you never have to worry about rolling off the end of the runway and getting run over by the airport. Compared to such challenges, crosswinds pale. For the rest of us, however, crosswinds are a factor, so we'd better learn how to figure them out.
Hello, Americans! Page 1. Maximum crosswind component. Did you know that several of our performance charts require us to determine the amount of headwind or tailwind component in order to determine our takeoff or landing distance? You will also find in most pilot operating handbooks a value listed for the maximum crosswind component the airplane is capable of handling. This limit is usually a function of structural limitations and pilot skill available for coping with the crosswind. The chart in Figure 29 allows us to determine the headwind and crosswind components. And now for the rest of the story.
Crosswind problem number 1. Assume you're departing on runway 30, as shown in Figure 30. The tower reports a wind from 330 degrees at 40 knots. What are the headwind and crosswind components associated with this wind? Runway 30 is aligned in a direction of 300 degrees. A wind from 330 degrees makes a 30-degree angle with the runway. It's reasonable to say that some of this wind imparts a headwind component and some a crosswind component. Do you remember Bud and Ed from Chapter 2, the bottom of page B3? It's the same principle. To find exactly how much there is of each, ask yourself what the angle is between the wind and the nose of the aeroplane. Obviously, the wind is 30 degrees off the right of the nose. The chart in Figure 30 shows degree calibrations in increments of 10 in a right direction. Assume the 0-degree mark represents the nose of the aeroplane. Start the problem there. Find the 30-degree diagonal line, point A. This represents the angle the wind makes with the nose of the aeroplane. Slide down this 30-degree line until reaching the 40-knot wind velocity arc, point B. Now, all you need to do is drop straight down to point D to determine the amount of crosswind blowing on the aeroplane. We have a right crosswind of 20 knots. To find the amount of headwind blowing on the aeroplane, simply move left horizontally to point C. This represents the amount of headwind blowing on the aeroplane. We have a headwind value of 35 knots. This headwind value is what we would use for any takeoff or landing performance computation. Crosswind problem number 2. Based on Figure 29, what is the crosswind component you can expect if landing on runway 18 with a tower reporting a wind of 220 degrees at 35 knots? Use Figure 31. First, ask yourself what the angle is between the wind and the nose. The difference between 180 degrees and 220 degrees is 40 degrees. Find the 40-degree diagonal line, point A, and slide down it until reaching the 35-knot wind arc, point B. You'll have to estimate where 35 is between the 30 and 40 arcs. Dropping straight down gives you a crosswind component of approximately 23 knots, point D. A headwind component of 27 knots also exists, point C. If your aeroplane was certified to handle a maximum crosswind component of 20 knots, would it be safe to fly? Probably not. This is another good reason to know how to use this chart. Crosswind problem number 3. Using Figure 29, determine the maximum wind velocity for a 30-degree crosswind if the maximum crosswind component for the aeroplane is 12 knots. The solution is provided in Figure 32. This problem requires us to work backwards. First, we know our aeroplane has a maximum crosswind component of 12 knots. Find this position along the bottom of the crosswind chart, point A. Move straight up until reaching the 30-degree diagonal line representing the wind's angle with the nose of the aeroplane, point B. At this point, ask yourself what wind arc you would be resting on if smaller wind arc calibrations existed. Parallel this arc around to the end of the scale, either direction. The maximum wind velocity should be 24 knots. Crosswind problem number 4. Using figure 29, find the amount of tailwind expected with a 30-knot wind from 135 degrees when landing on runway 27. The crosswind chart can also be used to find tailwind and crosswind components quite easily. The same procedure applies, except that we must find the angle between the wind and the tail, since we're talking about tailwinds. Figure 33 shows this problem. If you have trouble finding the angle between the wind and the tail, draw or find a circular compass rose with the 4 major directions, north, east, south, and west, on it as shown in figure 33. Aligned with runway 27 means you are pointed in a direction of 270 degrees. With wind from 135 degrees, remember wind always blows from somewhere, you have wind that makes a 45-degree angle between itself and the tail. Simply go to the crosswind chart and find the wind components for a 30-knot wind offset at a 45-degree angle. Point A shows a crosswind of 21 knots. Keeping your original picture in mind, you'll recognize this is a left crosswind. Point B shows a headwind component of 21 knots. We know, however, that this is actually a tailwind component. The crosswind chart wasn't necessarily built to find tailwind components, but if you understand the principle involved, it can be done. This is not to encourage you to plan for taking off with a tailwind. Such behavior is rarely prudent unless the tailwind is pretty minor. Making the forces be with you.
During Rod's youth, I was his school counselor. I attempted to predict what he might do with his life. I suggested life as a woodworker, then realized it meant handling sharp objects. No go. I suggested he would succeed at hubcap repair, but backtracked once I thought how distracting all the bright and shiny objects would be. Fortunately, I didn't predict well. This may be because nobody ever predicts someone will grow up to be a flight instructor. That's an inherently unpredictable outcome.
As a pilot, you can't afford to predict poorly when it comes to airplane performance. You need to become very familiar with the performance charts. Not only how to crunch numbers, but what those numbers really mean in terms of performance. Additionally, you need to understand the limitations these numbers impose on when and where flight can be safely undertaken. Remember, performance charts are prediction charts, and good pilots never leave to chance what they can predict. Post-flight briefing number 15-1. Advanced lesson in density altitude. Advanced density altitude problem number 1. In the aeroplane, finding pressure altitude is as easy as being a lifeguard in a car wash. Simply place 2/902 in the altimeter's Colesman window and read what the hands point to, the indicated altitude. This is your pressure altitude. Take the OAT and the pressure altitude and compute the density altitude by using the chart in figure 34. But how do you compute density altitude for an airport if you aren't there to set the altimeter to 2/902 inches of mercury and read the temperature? In other words, if you're reading the METAR for an airport and know the temperature and altimeter setting, can you still find its density altitude? Yes. Here's how. Let's start with a field elevation of 7,257 feet MSL. To the right of the density altitude chart is a vertical column showing altimeter setting versus pressure altitude conversion factors. Simply find the airport's current altimeter in the altimeter setting column and see what conversion factor must be applied to the altimeter reading to find pressure altitude. In other words, the altimeter should read the field elevation of 7,257 feet MSL with 30.20 inches of mercury set in the Colsman window. Moving the window's numbers down to 29.902 would simultaneously move the hands downward, make the indicated altitude read less. The conversion factor specifies how much the hands would move downward. Figure 34, position 1, shows that the conversion factor for an altimeter setting of 30.20 is minus 257 feet. You would add this value if it didn't have a minus sign next to it. Subtracting 257 from 7,257 gives you 7,000, which is the pressure altitude. Take the outside air temperature of 80 degrees Fahrenheit, 27 degrees Celsius, and a pressure altitude of 7,000 feet and, as shown by position 2 in figure 34, the density altitude is 10,000 feet. Even though your airplane is at 7,257 feet MSL, it's going to perform like it's at 10,000 feet MSL. Advanced Density Altitude Problem Number 2. Notice the diagonal line labeled Standard Temperature, running downward from left to right in figure 34. Sometimes we want to know the standard temperature for a specific altitude when standard conditions exist at sea level. Find any spot where the standard temperature line intersects a pressure altitude line and drop straight down to the temperature scale. This reading is the standard temperature for that pressure altitude. For example, on figure 34, find where the standard temperature line intersects the 4,000-foot pressure altitude line, position 3. Drop down to find the standard temperature of 45 degrees Fahrenheit, 7 degrees C, for that altitude. The same process works for all other pressure altitude values. Suppose I ask you to find the density altitude if standard temperature existed at 4,000 feet pressure altitude. Simply find where the standard temperature line intersects the pressure altitude line on figure 34 and move horizontally left to read a density altitude of 4,000 feet. You'll notice that whenever standard temperature exists at various pressure altitudes, the pressure altitude is always equal to the density altitude. I offer this only as an academic exercise because standard temperatures seldom exist at various pressure altitudes. I have been flying since 1970, and I have yet to see more than a handful of days having standard temperatures at sea level that stayed that way for any significant amount of time. Another important reason for offering this to you is because someone decided to put this type of question on the knowledge test. Don't ask me why either. Advanced Density Altitude Problem Number 3. What is your density altitude if the altimeter setting is 29.906 inches of mercury and the airport elevation is 3,293 feet with an OAT of 75 degrees Fahrenheit, 24 degrees Celsius? First, you must find the pressure altitude. With the altimeter setting in the altimeter window, the altimeter reads the true altitude, a field elevation of 3,293 feet MSL. The pressure altitude conversion for 29.906 inches of mercury is approximately halfway between that for 29.902 and 30.00, as shown in figure 34, position 4. Since the correction factors for 29.902 is 0 and 30.00 is minus 73, use a value halfway between them, or approximately minus 36. Subtracting 36 from 3,293 gives us a pressure altitude of 3,257 feet. Locating the pressure altitude value of 3,257 is easy if you draw the intermediate values between the 1,000-foot pressure altitude lines. Simply draw the 3,500-foot pressure altitude value between the 3,000 and 4,000-foot pressure altitude lines, as shown by position 5 on Figure 34. Now, draw an intermediate value between the 3,000 and 3,500-foot pressure altitude line. This represents the 3,250-foot pressure altitude value. Move up the 75 degree Fahrenheit, 24 degrees C line until reaching the pressure altitude line of 3,250, as shown by position 6 on Figure 34. This is real close to the actual pressure altitude value of 3,257 feet. Go across to the left and find a density altitude value of approximately 5,000 feet. Advanced Density Altitude Problem Number 4. Suppose you're flying a new Cessna 152 from an airport located at 9,702 feet MSL. The altimeter setting is 2960, and the OAT is 905 degrees Fahrenheit, 35 degrees C. That's hot for an airport that high. Better be careful. What is the density altitude at that airport? Using the pressure altitude conversion table in Figure 34, you determine that it's necessary to add 298 feet onto the true altitude to obtain a pressure altitude of 10,000 feet. 298 plus 9,702 equals 10,000. Using the OAT of 95 degrees Fahrenheit, 35 degrees C, and a pressure altitude of 10,000 feet gives you a density altitude of 14,700 feet. Chapter 16. Weight and Balance. Let's weight and balance. All aeroplanes have limits on the maximum weight they can carry and where that weight is placed within the aeroplane. Within these limits, aeroplanes perform normally. Outside of them, they behave erratically. Structural damage and in-flight stability are the two most important reasons why an aeroplane's weight is restricted and why the weight must be distributed in a certain way. Calculating whether the plane is within its stated restrictions is referred to as doing a weight and balance calculation. It's a crucial part of your pre-flight planning. Some pilots think the term is weight and balance, and that it refers to time spent in the aviation medical examiner's office before he invites you in and asks you to jump up and down on one foot without having a heart attack. A friend of mine found out the hard way what weight and balance really meant. Bob was a corporate pilot for a small Orange County firm. One day, the boss wanted to take the company's A-36 Bonanza on a ski trip. The plane was fully fueled when the boss arrived with enough ski gear to fill a 747. Taxiing to the run-up area, Bob turned the aft-heavy Bonanza into the wind and pressed the brakes. Suddenly, the nose started to rise, for no apparent reason. The aeroplane slowly and deliberately listed aft on the main gear. Smack! The nose pointed up, and the tail hit the ground. Bob was thinking about how he might gain admission to the Federal Witness Protection Program. He was embarrassed for not having done a weight and balance computation before the flight. He was even more embarrassed in not having said no to the obvious improper loading of an aeroplane. There was no telling how unsafe the aeroplane would have been had he taken off in this aft center of gravity condition. Bob gave the aeroplane full power, righted it, taxied back to the tie-down area, and unloaded the aircraft. He refused to fly unless the plane was operated within the proper weight and balance limits. This was an embarrassing lesson, but one he would never forget. Excessive weight and structural damage. Aeroplane wings are like bicycle tires in that both are designed to support a certain amount of weight. Too much weight could pop a bicycle's tire. Excessive weight can also damage a wing. Aeroplanes are designed to be flown up to a specific maximum gross weight. While it's possible to become airborne beyond this maximum certified weight, structural problems can arise when turbulence or high-G maneuvering enters the picture. Think about it this way. If an aeroplane is certified in the utility category, it can withstand 4.4 positive Gs without structural damage. If this aeroplane has a maximum gross weight of 2,000 pounds, its wings are certified to withstand 4.4 times the maximum gross weight of 2,000 pounds, or a total of 8,800 pounds. Distributing 8,800 pounds of force over the wings will bend them slightly. However, when the force is removed, the wings will flex back to their original position, and this is good. Now, suppose you take off in the same aeroplane with a gross weight of 2,100 pounds. No doubt the aeroplane easily becomes airborne when only 100 pounds over gross weight. But what happens if turbulence is encountered? If you experienced 4.4 Gs, the aeroplane's wings must now support 9,240 pounds of weight, 4.4 times 2,100. That's 440 pounds beyond the 8,800 pounds the engineers planned for. Now you're a test pilot and you are not getting hazardous duty pay. The risk of turbulence-induced damage has increased. Flying beyond the maximum weight limits presents other problems. For instance, the stall speed increases at heavier weights. More weight requires the wings to move faster through the air before they can develop the minimum lift necessary to sustain flight. It takes more runway to attain this faster speed. The takeoff distance increases. You won't find a performance chart for how much runway you'll need for takeoff when taking off over the maximum weight limit. More weight also means less climb performance, higher fuel consumption, reduced range, higher landing speeds, and longer landing distances. The list goes on and on. There is just no good reason to fly the aeroplane beyond its maximum gross weight limits. Pilots who insist on carrying all their friends in one aeroplane, regardless of their weight, should hang out with skinny people.
A friend of Rod's owned a small Cessna 150. This situation was unfortunate since he weighed several hundred pounds. He was 370. That's incredible when you consider 360 is a full circle. The only way he could fly the airplane and be within proper limits was to drain half the fuel from the tanks. This substantially shortened his range. Fortunately, his bladder was about the size of a BB, and shortened range was never really a bother.
Center of gravity. The center of gravity, CG, of any object is the point where, if an imaginary finger lifted it, the object would balance. See Figure 1. For an object whose weight is evenly distributed along its length, such as a popsicle stick, the CG is precisely at the center. For an object such as an aeroplane, where weight is not distributed evenly along its length, you have to calculate where the CG is. If an aeroplane will return unassisted to level flight after its controls are disturbed, it is said to have positive dynamic stability. If the aeroplane won't return to its original flight configuration, and in fact keeps diverging farther from it in a series of oscillations, it is said to be exhibiting negative dynamic stability. Engineers tell us that for an aeroplane to be positively stable, its weight must not be concentrated too far forward nor too far aft. These forward and aft weight limits are known as the center of gravity limits, as shown in Figure 2. Engineers know these limits because they have flight tested the aeroplane while wearing parachutes under variable load conditions. The results of this flight test information are provided to you in your aeroplane's weight and balance papers, always located in the aeroplane or in an approved flight manual specifically modified for that aeroplane. Beyond these limits, the aeroplane demonstrates negative dynamic stability in flight. For example, assume the aeroplane's weight is loaded within the allowable limits. If the controls are bumped as shown in Figure 3A, the aeroplane will oscillate up and down and eventually return to its previous level flight position. When the oscillations diminish in amplitude over time, it is a demonstration of positive dynamic stability. Now, assume the aeroplane is not loaded within its allowable limits and the controls are bumped, as shown in Figure 3B. The aeroplane exhibits negative dynamic stability because it moves farther away from its normal position.
Flying an airplane that is experiencing negative dynamic stability is about as safe as being the fourth crew member to beam down on a Star Trek mission. You know something bad is going to happen to that person. Negative dynamic stability means you're always having to fight for control of your airplane. In extreme cases, you may not be able to get the airplane under control. You never want to operate under these conditions. Loading an airplane properly prevents this problem. If the airplane would balance on your finger, anywhere between the forward and aft CG limits, it will be positively stable in flight. Assuming also that the airplane's weight doesn't exceed the maximum allowable limit.
Other CG considerations. Negative dynamic stability isn't the only negative outcome of loading an airplane outside its CG limits. The lift an airplane develops is spread over the entire surface of its wings from the leading to the trailing edge. Like weight, lift can be thought of as being focused at one point called the center of lift, Figure 4A. Also, the center of lift sidebar at top of the opposite page. Notice that the center of lift is located behind the CG. Since the aeroplane rotates about its CG, the wing's lifting force causes a constant nose-down tilting condition. This is why the tails of most airplanes, their horizontal stabilizers, are rigged to provide a downward force as shown in Figure 4B. A downward force on the tail compensates for the downward tilting force of the nose. This allows the aeroplane to remain controllable in flight. If you lost the tail in flight, you would lose control of the aeroplane. As the angle of attack increases, the center of lift moves forward, toward the front of the wing as shown in Figure 4C. As long as the center of lift is behind the CG, the aeroplane still has a forward pitching tendency. This is a good thing, since this nose downward pitching tendency acts to automatically reduce the angle of attack. The aeroplane naturally wants to keep itself away from high angles of attack where stalls occur. It also wants to automatically reduce its angle of attack in the event of a stall. Moving the CG rearward. Beyond the aft CG limit is very dangerous. If the CG is too far aft, the center of lift at high angles of attack might move ahead of the CG as shown in Figure 4D. Now the airplane wants to pitch up and increase its angle of attack. You might have to apply a lot of forward elevator control to get the nose to pitch down. Under certain conditions, slow airspeeds and high angles of attack for instance, the airplane may not respond.
An aft CG condition can lead to violent stalls and flat spins. These are not good things. Dude, check it out. Fly like this, and you feel like a chicken with the colonel close behind. Woo. When flown within proper CG limits, however, airplanes are perfectly safe. A pilot's job is to always make sure that the CG remains within the limits. An aft CG tends to give you lower stick forces, meaning that a slight touch on the controls causes a large and sometimes uncontrollable oscillation of the nose. It's similar to the first time you drove a car with power steering. It's very easy to over-control. Ooh. The airplane can be easily overstressed in this condition.
Aeroplanes loaded beyond the forward CG limit often fare no better. With the CG located ahead of the forward limit, Figure 5a, an excessive tail-down force is required to keep the nose up. During landing, as the aeroplane slows, there may not be enough airflow over the tail to generate this tail-down force. You may find yourself needing full rearward elevator pressure just to keep the nose up during the flare, if it will stay up at all, as shown in Figure 5b. Excessive forward loading causes higher stalling speeds, decreased performance, and higher stick forces.
Now, folks, correct placement of the CG is obviously very important. But how do you measure its location? You can't go stick your finger under an airplane and lifting it up every time you need to do a weight and balance. You can, however, use that dexterous digit to push calculator buttons, or a pencil, and find the CG through the magic of mathematics.
Just a moment. To locate the center of gravity on an airplane, you need to understand the concept of moment, or tilting force. An airplane moment is different than a Kodak moment, or a moment of time. A moment, as we're using the term here, is nothing more than a measure of the tilting force that weight imposes on an airplane. Figure 6a shows two 10-pound blocks placed on a plank at equal distances of 5 feet from the balance point. The plank is perfectly balanced because of where the weights are placed. The plank's CG, or balance point, is located at the fulcrum, the small triangle. It's obvious that block K causes the plank to tilt counterclockwise to the left. Block R, on the other side of the plank, causes a similar tilt but in a clockwise direction to the right. It's this tilting force that engineers refer to as the plank's moment. Since the plank balances, it should be obvious that the opposite tilting forces, or moments, caused by both blocks are opposite yet equal. They cancel out each other, and the plank remains balanced at the fulcrum. Seeing is believing. But how do we prove this without actually performing the experiment? We can prove that the plank is balanced by multiplying the individual weights by their distances from the fulcrum, then comparing these values. Before we do this, let's define a few terms. The word weight is self-explanatory. It's what you measure with a scale. The distance that the weight is placed from the fulcrum is called the arm. The tilting force resulting from a certain weight being placed at a specific arm or distance from the fulcrum is called the moment. To determine the moment, we simply multiply the weight times the arm. Figure 6b shows this formula.
At this point, most people say, "Dude, check it out. You're using higher math? Wait just a moment." That's probably how they got the name for tilting force. Not really. Many people treat math like the handle of a bathroom door. In their mind, that handle is a petri dish on a hinge. Something to be avoided. Don't worry. The worst math you'll have to do is division. On the private pilot knowledge exam, you are welcome to use your calculator.
In Figure 6a, to obtain block K's moment, simply multiply the weight of block K times the arm, its distance from the fulcrum. You obtain 10 pounds times 5 feet equaling 50 foot-pounds of tilting force in the left or counterclockwise direction. We'll call this the negative direction. Do the same with block R, and you get 10 pounds times 5 feet equaling 50 foot-pounds of tilting force in the right or clockwise direction. We'll call this the positive direction as shown in Figure 6b. It's obvious that both tilting forces or moments are equal and opposite in direction. This is mathematical proof that the plank balances at the fulcrum. Since the moment is a product of a weight and a distance, the units of foot-pounds or inch-pounds follow its numerical value. Now, let's make the problem a little more interesting. This is your instructor's way of saying, I think you'll be stumped if I don't show this to you. Suppose we have two different weights located at different positions along the plank as shown in Figure 7. Notice that the moments for block Q are equal and opposite to the moments of block P. The plank balances at the fulcrum. Despite the differences in weights and their positions along the plank, we can easily, with math, determine whether the plank will balance or tilt. Now that you understand the concept of moments, let's find the center of gravity when the weights and moments are known. Figure 8a shows the same plank without a fulcrum. Our objective is to find where we should place the fulcrum so that the plank will balance. On the left side of Figure 8a is a datum line. This is nothing more than an arbitrary vertical reference line from which we'll measure our distances.
Daniel-san, the datum line is easy to understand. For instance, I might ask you what your distance is from the Hawaiian island of Molokai, our datum reference. If you said 4,000 miles east, then I'd have an idea of your position. If you said you were 1,500 miles east of San Francisco, another datum reference, I'd still have an idea of your position, as long as I know which datum is being referenced.
To find the center of gravity of the two weights in Figure 8a, we'll find the moment of block Z about the datum line. Simply multiply block Z's weight times its arm, its distance from the datum line, our new measuring reference. Do the same with block W. These calculations are shown in Figure 8b. Remember, we're trying to find the point past the datum where these weights balance if a finger or fulcrum were placed under the plank. Now add all the weights and moments up as shown in Figure 8b. These are the total weights and the total moments produced by these weights. Dividing the total moments by the total weights as shown in Figure 8c gives you the arm distance at which the plank balances. This distance is 10 feet to the right of the datum line. The arm represents the CG location of these two weights. Notice how the CG is located in the same place in Figure 8d as it is in Figure 7. The general rule in finding the CG is to add up the individual weights, find the moments of these weights about the datum or reference line, then divide the moments by the total weight. This gives you the arm or the current CG location in inches or feet past the datum line. Finding the CG of an aeroplane is done exactly the same way. Some aeroplanes have datum lines located at the firewall or on the tip of the spinner, as shown in Figure 9. The datum line can be placed wherever the engineer desires. It's a personal decision, much like how a flight instructor dresses. Instructors are not snappy dressers, which explains why they are always asking their spouses, "Honey, does plaid go with a propeller hat?" When datum lines are located at the firewall, then everything to the left of the datum line produces a negative value, and everything to the right a positive value. For instance, oil, located to the left of a firewall datum line, produces a moment with a negative value. The negative moment must be subtracted from the total moments before dividing. Don't subtract the weight of the oil, since it's part of the total weight of the aeroplane. We're almost ready to work an actual weight and balance problem, but first we need to add a few more terms to our vocabulary. 1. Maximum takeoff weight. This is the maximum weight with which you can take off. This is sometimes referred to as the maximum certificated gross weight or maximum gross weight. The latter term is often shortened to max gross by pilots, making it sound like it's someone they know. This weight is based on a structural limitation of the aeroplane. 2. Empty weight. The weight of a standard aeroplane, including all non-drainable fluids. It includes unusable fuel, hydraulic fluid, and non-drainable oil, and all permanently installed equipment, for example, radios, etc. For some airplanes, the term basic empty weight might include engine oil. You should check your airplane's weight and balance information to specifically identify when oil is included in the basic empty weight. This information is always located inside the airplane and can be seen in Figure 10. 3. Useful load. The weight of the pilot, passengers, baggage, cargo, usable fuel, and oil, if not included in the basic empty weight. You can also think of the useful load as the difference between the maximum takeoff weight and the empty weight. A very important formula to remember is the empty weight plus the useful load equals the gross weight.
Aviation fuel weighs 6 pounds per gallon, and oil weighs 7.5 pounds per gallon. Watch out. That's per gallon, not per quart. It's important to know the exact weight of fuel since there are times when the airplane must be defueled to meet the maximum takeoff weight requirements. Many times airplanes are fueled the day or night before your flight. Deciding to carry an extra passenger or extra baggage the following day might require removing a certain amount of fuel from the tanks. The gas boy or girl, internal combustion liquid petroleum allocation manager, can do this.
For example, if your airplane is 110 pounds over the maximum takeoff weight, how much fuel must be drained to be within legal weight limits? The answer is approximately 18.3 gallons. Simply divide 110 by 6, pounds divided by gallons of fuel. Once you know the proper steps to take in solving a weight and balance problem, you'll whip right through the calculations. Believe me when I say it works. It's like using a sunblock with an SPF rating of 2047. That stuff works. It not only blocks the sun, it makes it rain. Don't wait to balance. Let's apply our newfound knowledge and solve the simple weight and balance problem shown in Figure 11a. Figure 11a provides the aeroplane's empty weight along with the arm and moment associated with this weight. Figure 11b shows a visual representation of what the aeroplane loading might look like. The empty weight arm is nothing more than the point where the weight of the empty weight is concentrated, its center of gravity. This arm is used in computing the empty weight moment. Since the empty weight moment is given to you in the aeroplane's weight and balance papers, you need not calculate it. The pilot and front passenger weigh a combined 380 pounds. They will both sit at an arm or distance of 64.0 inches aft of the datum. What moment do the pilot and passenger produce? Multiply their weight and arm together. You should get 24,320 inch-pounds. Fuel is next. We have 30 gallons of usable fuel on this flight. How much does that weigh? Multiply 30 times 6 pounds per gallon, equaling 180 pounds. The fuel tanks are located at an arm of 96.0 inches aft of the datum. What moment does the fuel produce? Multiply 180 pounds times 96.0 inches, equaling 17,280 inch-pounds. To find the CG for the loaded aeroplane, you must divide the total moments by the total weight. Remember, all three arms that are shown in the middle column of Figure 11A are only used in computing the moments. The arms aren't added, since this would serve no purpose. The next time that you will use the concept of arm is when you divide the aeroplane's total moment by its total weight. The arm or distance is now the point where the full aeroplane would balance, in other words, its center of gravity. Weight times arm equals moment. Arm, the center of gravity, equals total moments divided by total weight. The total weight is 2,070 pounds. The total moments are 193,673 inch-pounds. Divide the total moments by the total weight to get the CG arm, the distance from the datum where the weights balance. Divide 193,673 by 2,070, equaling 93.6 inches, the center of gravity, as shown in Figure 11B. Considering that forward and aft CG limits are usually expressed in inches past the datum line, we can easily tell if the CG is within the appropriate limits for safe flight. Suppose the forward CG limit was set at 89.0 inches and the aft limit was 97.3 inches. In this instance, the aeroplane falls within the proper CG limits. Now that we understand how to determine the CG from weights and moments, let's try to work a weight and balance problem from an actual airplane. Figures 12 and 13, previous page, provide you with information that might come from a typical airplane. As you'll soon see, doing a real weight and balance is easier than it looks. Figure 12 provides us with the moments for the variable weights of occupants, usable fuel, baggage, auxiliary fuel, and oil. Oil for this aeroplane is included in the basic empty weight. The bottom right-hand corner, block G, informs us about the forward and aft CG limits for variable weight conditions. What's nice about this chart is that in many instances, it's often not necessary to do multiplication to find the moments. For example, assume you wanted to find the moment of the front seat occupant weighing 320 pounds. That's two people, not one big guy. Look in the weight column in block A and find the moments for any weight combinations that add up to 320. For instance, 120 pounds produces a moment of 102, and 200 pounds produces a moment of 170. Adding these together gives you a moment of 272. Notice that block A shows that all the moments are divided by 100. Why? This is known as a reduction factor, and it makes large moments easier to work with. Since the front seat arm is 85, you can assume the distance is in inches. Multiplying 85 inches times 320 pounds equals 27,200 inch-pounds of moment. When divided by a reduction factor of 100, we still arrive at a moment of 272 inch-pounds. 27,200 divided by 100 equals 272. Of course, when you're done computing all the moments, you'll want to multiply the total moments by 100 to be able to compute the actual CG. Or you can move the decimal 2 places to the right. It's the same thing. Suppose the weights are between the values shown in the column, such as 295 pounds. There is no moment value listed for 295 pounds. The best way to handle this is to do the math and simply multiply the weight times the arm for that location to get the moment. Remember the reduction factor of 100. The same procedure for finding moments is used for rear seats, Block A, usable fuel, Block B, baggage or fifth seat occupant, Block C, auxiliary wing tank fuel, Block D, and oil, Block E. Remember, the weight of the oil and its moment are included in this aeroplane's basic empty weight. Therefore, don't include oil in this weight and balance problem. Block F provides you with the basic empty weight and its moment divided by the reduction factor of 100. Block G informs you of the forward and aft CG limits for variable weight conditions. Okay, let's try it. Basic weight and balance, problem number 1. Using the weight and balance information in figures 12 and 13 and the loading information given below, determine if the aeroplane's weight and balance is within safe limits. Front seat occupants, 320 pounds. Rear seat occupants, 295 pounds. Fuel, main wing tanks, 44 gallons. Baggage, 56 pounds. Before you start, let's remember the big picture here. What you're going to do is find the tilting force produced by all the individual weights to be carried on the aeroplane by using the useful load weights and moments chart, figure 12. Then you'll add all these weights together and add all the moments together. Take these two sums over to the moment limits versus weight chart, figure 13. This chart lets you determine if the combination of total weight and total moments allows the aeroplane to operate within its allowable CG limits. Now don't worry, I'm going to walk you through this first problem in great detail as shown in figure 14. Not only will I show you how to proceed step by step, but I'll give you a visual representation of what the loaded airplane would look like in figure 15. Okay, are you ready? Now, go to figure 14 and follow each step in the solution of this problem. Step 1. See figure 12F to find the basic empty weight and its moment. Step 2. See figure 12A1 to find the moment for 120 pounds and 200 pounds of front seat occupants. Step 3. See figure 12A2. Since the exact weight of our rear seat occupants doesn't appear in the table, we must multiply their weight times the arm of the rear seat of 121 inches. This gives the moments of the rear seat occupants. Step 4. See figure 12B to find the moment for 44 gallons of fuel. Note, don't forget to use the listed weight of the fuel, 264 pounds. In other words, don't list the gallons in the weight column. Step 5. See figure 12C to find the moment for the baggage. Since no moment is listed for 56 pounds, multiply this times the arm of 140 inches and divide by 100 to obtain the moment of the baggage. Step 6. See Figure 12E. The note says that oil is included in the basic empty weight, so we don't need to do anything here. Step 7. Add the total weight and the total moments. You don't need to add the total arms, since this is meaningless. Step 8. Move the decimal place of the total moments 2 digits to the right to correct for the reduction factor of the moment divided by 100. Step 9. Compute the CG by dividing the total moments by the total weight. Step 10. Determine if the CG and weight fall within acceptable limits by looking at Figure 12G. Now that wasn't too bad, was it? I'm going to show you how to make solving this type of problem even easier. But first, here are a few additional points to remember when doing this type of problem. To compute the moment of the front seat occupants, you need to refer to Figure 12, Block A, Section Number 1, and find the moments for 200 pounds and 120 pounds. Then add these together. You do this because there is no posted moment for 320 pounds. The weight of the baggage isn't listed in Figure 12, Block C. You can find its moment, however, by multiplying the arm of 140 by 56 pounds. When preparing to divide the total moments by the total weights, don't forget to move the decimal of the total moments over 2 places to the right to compensate for the reduction factor of 100. The result of Figure 14, step number 9, indicates that at a weight of 2,950 pounds, we have a CG of 83.4 inches. Figure 12, Block G, indicates that we are right at the maximum gross weight of the aeroplane for takeoff or landing. At a weight of 2,950 pounds, our CG of 83.4 inches falls within the posted forward and aft limits. We are legal and safe to fly. Figure 15 shows a pictorial representation of how this aeroplane is loaded. What if our totaled weights were different than the limits shown in Figure 12, Block G? Fortunately, the pilot's operating handbook or the plane's weight and balance papers come with a moment limit versus weight chart to help determine if the aeroplane is within weight and balance limits. Figure 13 shows such a chart. This chart makes the computations easier since it allows you to determine proper loading without having to divide the total moments by the total weights. In other words, you compare total weight with the total moment to determine if the aeroplane is within proper CG limits. For instance, in this problem, the total moments were 2,459.4, moment divided by 100, and the total weights were 2,950 pounds. Compare the weight against the minimum and maximum moment limit, Figure 13, Position A, and you'll see that we still fall within acceptable limits for flight. You may be wondering, how do I know what items to include in the weight and balance calculations? That's an excellent question. The following letter sequence provides you with an easy way to remember the items to include in a weight and balance calculation. EPR, FBO. This stands for Every Pilot Regrets Flying Barely Overweight. E is for Empty Weight. P for Pilot and Front Passenger. R for Rear Seat Passenger. F for Fuel. B for Baggage, and O for Oil, if not included in the basic empty weight. When given a weight and balance problem to solve, simply list these letters vertically and write W times A equals M. Weight times arm equals moment, equation across the top of the page as shown in Figure 16. Then proceed to fill in the appropriate weights and moments. Basic weight and balance problem number 2. Okay, let's try a problem similar to the previous one. Take a piece of paper and draw the acronym EPRFBO on the left-hand side and W times A equals M across the top. Use the loading information below and figures 12 and 13 to determine if the weight and balance is within safe limits. Front seat occupants, 415 pounds. Rear seat occupants, 110 pounds. Fuel, main and auxiliary tanks, 63 gallons, both tanks full. Baggage, 32 pounds. Figure 17 shows the numbers you should have derived. Consulting block G in Figure 12, we see that the aeroplane's weight is within limits, but the CG of 81.0 inches is 1.1 inch forward of the allowable limit. We can come to the same conclusion referring to Figure 13, Position A. The moments don't fall within the allowable minimum and maximum shown on the chart. For the aeroplane to be legal for flight, we'd need to increase the total moment. In other words, we'd need to move some weight rearward. We can't add more weight because we're already at the aeroplane's maximum weight limit of 2,950 pounds. We might solve the problem by rearranging some of the passengers or moving some baggage.
Now, there are formulas for figuring out how much weight to move and what distance to move it. They are, however, beyond the scope of this book. Personally, I would recommend just taking a guess at how much movement or reduction in weight is necessary to put the airplane within the allowable CG limits. Then working another problem to see if the results are successful. This doesn't take long at all when you're changing only one or two variables. Now you're doing well. Once you understand the basics, the rest of the weight and balance problems should be fairly easy. There is, however, no better way to learn to do these problems than to jump in and give them a try. So let's move on to something known as weight change problem.
Weight change, problem number 3. Upon landing, the front seat passenger of 180 pounds departs the aeroplane, after it comes to a stop, fortunately. The rear seat passenger, at 204 pounds, moves to the front passenger position. What effect does this have on the CG if the aeroplane weighed 2,690 pounds and the moment divided by 100 was 2,260 just prior to the passenger transfer? We'll use the same weight and balance information given in Figure 12 and 13 to solve this problem. Before you proceed, I want you to think about the problem in a step-by-step way as follows. Step 1. To determine the final CG, you need to know the aeroplane's total weight and total moment. Ask yourself how much the total weight of the aeroplane changes. Step 2. If any weight moves on the aeroplane but doesn't exit or enter the aeroplane, its moment changes. In other words, the weight's moment before moving must be subtracted from the total moment. Then its new amount, based on its new location, must be added to the total moment once again. Step 3. Divide the total moment by the total weight to obtain the new CG. Step 4. Go back to the original problem and make sure you answer the question that was asked. Figure 18 shows how to proceed with the problem using the steps listed above, Go back and review the other problems to get a good feel for how this one was solved. I do hope you believe me when I say that once you practice a few more problems, weight and balance is going to be a snap. Problem number 3 dealt with weight change. Every time you fly, you'll need to consider similar problems since the consumption of fuel changes and shifts the aeroplane's CG. Problem number 4 deals with the changing CG based on the burning of fuel. Fuel burn, weight and balance. Problem number 4. What effect does a 35-gallon fuel burn in the main tanks have on the weight and balance if the aeroplane weighed 2,890 pounds and the moment divided by 100 was 2,452 at takeoff? Refer to the weight and balance information in Figure 12 and 13 to solve this problem. Keep in mind that the same principles used in problem number 3 are used in solving this problem. Fuel burn is nothing more than a weight and moment change problem. In this instance, weight, the fuel, is leaving the aeroplane, therefore the moment is also changing. Figure 19 shows how to proceed with the problem. It's important to compute the CG change for fuel consumption. As is evident from this problem, the CG shifted aft as fuel was consumed. It may be necessary to shift weight in flight or prior to takeoff to compensate for this type of problem. Expect to have a problem like this when the CG, prior to takeoff, is near the aft or forward limit. In the following problem, we have an aeroplane that's out of its safe CG limits and can't take off. The weight is within limits, but the CG is forward of the allowable limit. This doesn't mean you can't fly. All you usually need to do is move some of the weight around to place the CG within its acceptable limits. Knowing how to calculate this is a valuable skill to have. Weight shift problem number 5. With the aeroplane loaded as follows, what action must be taken to place the aeroplane within the proper weight and balance limits? Refer to the weight and balance information in Figure 12 and 13 to solve this problem. Front seat occupants, 411 pounds. Rear seat occupants, 100 pounds. Main wing tanks, 44 gallons. Figure 20 shows how to proceed with this problem. Using the moment limits versus weight chart in Figure 13, see position D, the aeroplane is determined to be out of CG limits. In other words, our moment is smaller than the minimum moment required for flight. This means there isn't enough weight far enough aft of the datum to get the aeroplane within CG limits. How can we solve this type of problem?
Well, that's fine. That's just fine. I'm not going to give you the old veteran flyer routine. I just want you to know I've been flying for some time now, and it hasn't always been for crummy outfits like this one. You might think about transferring some fuel from the main tanks to the auxiliary fuel tanks, but that just won't help the problem. Closely looking at the difference in the moments produced by the main and the auxiliary tanks for similar weights, there isn't much difference. Even if enough fuel was transferred to get the airplane within CG limits prior to takeoff, what's going to happen as the fuel is used? You say that's fine, but it isn't. The airplane will still lose weight and the resulting moment will still be too small.
The best thing to do when you have a forward CG is to try and move weight aft, like a passenger. Of course, only move them aft if there is a seat in back, otherwise they might be reluctant to go. If that's not possible and the aeroplane isn't near gross weight, add some weight to the baggage compartment. Let's try adding 100 pounds of weight to the baggage compartment and see if that brings us within CG limits. Step 3 in Figure 20 shows the results of adding this weight. Looking at Figure 13, position E, We now see that the CG is within allowable limits. I'd still be cautious and determine what the CG will be as I burn off fuel. That's why I do another weight and balance problem based on the amount of fuel I expect to consume during my trip. See previous problem number 4. A different type of weight and balance chart. Another type of weight and balance configuration exists for aeroplanes. In fact, for most of the smaller aeroplanes we fly, this configuration shown in Figure 21A and B is quite common. What makes this configuration so interesting is that there is no multiplication used in finding moments. The loading graph in Figure 21A has weights along the vertical axis and moments divided by 1,000 along the horizontal axis. A reduction factor of 1,000 is used for the moments, but, as you'll see, you don't have to worry about using a reduction factor when using this format. To find the moments for specific weights, simply proceed horizontally along the weight lines. When reaching the desired diagonal line for pilot, passenger, fuel, or baggage, drop straight down to find the moments. That's easy. When the total moments and weights are tallied, simply proceed to the center of gravity moment envelope shown in Figure 21B. Compare weights and moments to see if they fall within the envelope. Notice that this aeroplane has both a normal and utility category envelope. Depending on the aeroplane, the CG must fall within the utility CG envelope for certain flight operations to be performed, such as spins. Using this simple format, you'll be able to do weight and balance problems while using only 50 cc's of your turbocharged 1400 cc brain. Weight and balance problem number 6. Using the aeroplane loading information shown in Figure 22A, determine if the aeroplane is within its proper CG limits. Figure 22B shows the solution for this problem. Figures 23A and 23B show the solution on the loading graph and CG moment envelope. This is a relatively straightforward weight and balance problem, nothing tricky here. You should use caution, however, when calibrating moments from weights in Figure 21A. It's very easy to move up or down a line and end up with an incorrect moment. Watch the calibration for the individual chart lines. In Figure 21A, notice that each line along the weight vertical scale is calibrated in tens of pounds. Each line along the moment horizontal scale is calibrated in values of 1/2. Weight and balance problem number 7. The next problem in Figure 24A requires you to determine the maximum amount of baggage that can be carried in the aeroplane after all the other items have been loaded. Solving this problem simply requires you to find the current loaded weight of the aeroplane and subtract that from the maximum allowable weight. The difference is the amount of baggage, or any other item you're interested in, that can be carried on board. After you determine the allowable weight of baggage, you must make sure that carrying this weight still keeps the aeroplane within its proper CG limits. Figures 24B, 25A, and 25B show the solution to this problem. Weight and balance problem number 8. Figure 26 is our final problem. This problem is similar to problem number 7. Instead of finding the maximum amount of baggage that you can carry, this problem asks you to determine the maximum amount of fuel that can be carried aboard the aircraft for takeoff. It's solved in precisely the same way as problem number 6. Solving this problem simply requires you to find the current loaded weight of the airplane without fuel and subtract that from the maximum weight allowable for that airplane. The difference is the amount of fuel that can be carried aboard. After you determine the allowable weight of fuel, you must make sure that carrying this weight still keeps the aeroplane within proper CG limits. Figures 26, 27A, and 27B show the solution to this problem. Chapter 17. Pilot Potpourri. Neat Aeronautical Information. The time has come, the walrus said, to talk of many things, of shoes and ships and sealing wax, of cabbages and kings, and why the sea is boiling hot, and whether pigs have wings. Lewis Carroll, Alice in Wonderland. Pigs do not have wings, aeroplanes do. We're almost done, so now the time has come to speak of many things. In this chapter, I'll present some information morsels on a variety of topics, all of which I think you will find interesting, useful, and helpful to your flying. As you read these munchies, keep in mind that part of the fun of aviation is that the learning never stops. New ways of doing old things always emerge, as do new ways of doing new things. We're continually learning new information about human performance and equipment capability. Flight instructors like to say that earning your private pilot license is really getting a license to learn, and I think there's a lot of truth to that. Taking Aim, the Aeronautical Information Manual. One night my wife awakened me from a sound sleep because she'd heard a noise. "Rod," she said, "I think there's someone outside." Jostled out of REM sleep, I replied, "Honey, that's where they're supposed to be, outside. If they come in here, then we'll go outside." Without the full use of my faculties, brain not warmed up, the answer seemed perfectly reasonable to me. After all, everything has its place, correct? This is especially true with aviation information. If you're ever looking for the source of aviation's wisdom, common sense, and good operating principles, it has its place in the Aeronautical Information Manual, AIM. Those who've been around aviation a while knew the AIM under its maiden name, the Airman's Information Manual. In 1995, as part of a government-wide effort to eliminate gender-specific terms wherever possible, the Airman's Information Manual became the Aeronautical Information Manual. Fortunately, the aim was the same. The AIM is both Bible and Quran for pilots. It is the official source of information on a variety of subjects, all of great importance to aviators, and of late has improved considerably in appearance. It's now replete with color illustrations. I encourage you to subscribe to this publication, available from the Superintendent of Documents, P.O. Box 371954, Pittsburgh, Pennsylvania, 15250-7954. Many of the topics and ideas in this chapter are drawn from the AIM, which also contains details about everything from the signal width of an instrument landing system to details on the right way to interact with controllers.
Hello, Americans! Page 2, Fitness for Flight. All pilots, except those flying gliders and free balloons, are required to hold a valid medical certificate to act as pilot in command. You do not have to be Joe Weider, a one-time muscle man whose chest looked like an inverted pyramid, to pass the medical. However, certain conditions are disqualifying. Personality disorder, manifested by overacts. I'm referring to the serious ones, not selfishness or rudeness. Alcoholism, drug dependency, epilepsy, unexplained disturbance of consciousness, and heart attack, to name a few. Fortunately, pilots not meeting the medical standards can still be qualified under the special issuance provisions of the certification process. This is why it's best for student pilots to visit an aviation medical examiner as soon as possible after starting flight training. If there's going to be a problem getting a medical certificate, it's better to know about it early.
One thing you should be aware of is that the FARs prohibit you from acting as PIC if you have a known medical condition or worsening of a medical condition that would make you unable to meet the standards for a medical certificate. Just because you passed the medical in May does not mean you are legal in June if you had a heart attack in between. I had a friend who flight instructed for 2 months with a partial cast on his right leg. I suppose he shouldn't have been flying, but he did it anyway. He rationalized his decision by saying that he could still pass the medical. I suggested that if the doctor made him jump up and down on that leg for 20 seconds, he might have jackhammered himself into the floor below. The only good thing about having a heavy cast on his right leg was that he didn't have any trouble using enough right rudder. Illness. Be cautious if you're thinking about flying when ill. Many day-to-day illnesses will degrade your performance to unsafe levels. Judgment can be impaired, along with memory, the ability to calculate, and alertness. Beyond difficulty in filling out the Hobbs meter sheet, these problems are serious and could impair your ability to safely fly an airplane. You owe it to yourself and your passengers to be as fit as possible when you park yourself in the pilot seat of any airplane. Medication. If you don't think your performance can be degraded by over-the-counter medication, then you've probably never taken any. Look on the back of a box of antihistamines. It usually says, "Don't operate heavy equipment after using this drug." Does that mean you shouldn't take the family bulldozer to the market for some milk? Implied in this statement is a warning of performance degradation. Certainly this applies to airplanes as well as to cars and bulldozers too. For instance, some antihistamines can make a pilot more susceptible to hypoxia, oxygen deficiency. You are likely to feel the effects of oxygen deficiency at lower altitudes, and most antihistamines can cause some degree of drowsiness. While antihistamines are an obvious no-no, many drugs have less obvious effects that can cause a decrement in pilot performance. Quite frankly, if you're taking any medication, call your family physician to determine its side effects. A call to your aviation medical examiner might be an even better idea, because AMEs are often familiar with medications' effects which pose a risk to pilots, even though physicians might not think of them as side effects or even be aware of them. Alcohol. Don't fly high. Don't even think about mixing flying and alcohol. Your behavior is easily impaired by alcohol consumption. For instance, an older mariner who had spent many years on boats decided to take flying lessons. He showed up drunk for a flight, walked over to the airplane, untied all the ropes, threw them in the air and yelled, "Cast off!" A very embarrassing situation. As little as 1 ounce of liquor, 1 bottle of beer, or 4 ounces of wine can impair flying skills. Keep in mind that legally you may not operate an aircraft within 8 hours of having consumed any alcohol. Also, be aware that the effects of alcohol can linger long after 8 hours. Judgment, coordination, and other items you really want to have available as a pilot can be impaired even when you don't have an obvious hangover. It's usually best to wait at least 12 to 24 hours between the bottle and the throttle, depending on the amount of alcohol consumed. Hypoxia. Low O2. Hypoxia is a state of oxygen deficiency in the body sufficient to impair function of the brain and other organs. While the percentage of oxygen in the atmosphere doesn't change with an increase in altitude, it stays about 21%, the amount of pressure that forces oxygen into our body decreases, causing hypoxia. Because of this lower pressure, pilots flying at higher altitudes, 50,000 feet and above, often wear pressure suits. That's pressure suit, not power suit. In other words, double-breasted black suit with red tie, which would look pretty dumb at 50,000 feet anyway. The effects of hypoxia occur at altitudes as low as 5,000 feet, beginning with a deterioration of night vision. The eyes require a great deal of oxygen to function properly. They are one of the first organs to experience the effects of reduced oxygen within the body. Other significant effects of hypoxia often don't occur in the normal, healthy pilot below 10,000 feet. If, however, you smoke, then all bets are off. Smoking reduces the altitude at which the effects of hypoxia are experienced. It also increases the chance of your power suit catching on fire. Above 10,000 feet MSL, most individuals begin to experience some decrease in their judgment, memory, alertness, and coordination. The ability to calculate also becomes impaired to some degree for most individuals with the increasing effects of hypoxia.
You are bound to enter another dimension, a dimension out of sight, sound, or mind, the dimension of hypoxia. What makes hypoxia such a serious problem is that its effects are usually quite difficult to recognize, especially when they occur gradually. Headache, drowsiness, dizziness, and either a sense of well-being, otherwise known as euphoria, or belligerence can occur. You sometimes get a similar feeling when studying the Federal Aviation Regulations, especially the headache and the dizziness part.
The higher the altitude, the less time it takes for hypoxia to start robbing you of your flying faculties. In fact, it's not unusual for pilot performance to seriously deteriorate within 15 minutes at 15,000 feet. Figure 1 identifies the time of useful consciousness at various altitudes without the use of supplemental oxygen. Preventing hypoxia means avoiding higher altitudes unless you have the use of supplemental oxygen. It's recommended that you avoid flying at more than 10,000 feet during the day or more than 5,000 feet at night without the use of oxygen. Understand that this recommendation is lower than those limits required by FAR 91.211. Nevertheless, it's best to follow the conservative path. Pilots using supplemental aviation breathing oxygen need to avoid using greasy or oily rags around oxygen systems. Petroleum-based products and oxygen don't mix. They are a very dangerous combination that could cause a fire, explosion, and definitely serious injury. In fact, the military recommends that their pilots not use lip balm, chapstick, when they plan on using oxygen. Why? Because lip balm is petroleum-based. Perhaps that's why it sounds like lip balm. It's possible you might have lips heavily coated with lip balm, go on oxygen, hear a boom, then spend the rest of the flight looking around the cockpit for your lips. Can you imagine how difficult it will be to call the tower on the radio without your lips? Hyperventilation. I once asked a student in class what it means if a pilot starts panting or breathing quickly and shallow-like. This fellow replied, "It means he's been eating milk-bone dog biscuits." This was the same guy from the airspace chapter who had a Coke machine fall on him. Hyperventilation is abnormally quick, shallow breathing. It can happen when a person is scared, tense, or otherwise stressed. The rapid breathing has the effect of changing your blood chemistry by expelling a more than normal amount of carbon dioxide. The level of carbon dioxide is one of the signals the body uses to regulate breathing. The symptoms resulting from hyperventilation can include lightheadedness, suffocation, drowsiness, tingling in the extremities, and coolness. Incapacitation in the form of a lack of coordination, disorientation, and painful muscle spasms can eventually result, as can unconsciousness. You can reduce and eliminate the symptoms of hyperventilation by bringing the rate and depth of your breathing under control. In other words, by purposely slowing your breathing rate, you allow the necessary carbon dioxide to rebuild within the body. These symptoms will disappear within a few minutes. Talking loud is one way to overcome the effects of hyperventilation. This forces you to wait longer between breaths and builds up the body's carbon dioxide level. It also causes other people to stare and point at you. Some people recommend breathing into a paper bag to help build up the carbon dioxide. Simply hold it over your nose and mouth until the symptoms subside. Don't put the entire bag over your head, even if you poke holes out for the eyes. This is no time to get a little instrument work in, and besides, it scares the passengers. The early symptoms of hyperventilation and hypoxia are similar. They can even occur at the same time. You'd definitely be having a bad flying day, and M&Ms would probably melt in your hand. If you find yourself using an oxygen system because of hypoxia or hyperventilation, set the oxygen regulator to give you maximum oxygen flow. This may appear contradictory to you. After all, if we are hyperventilating, we need carbon dioxide, not oxygen. The problem is that you may not be sure which it is, hypoxia or hyperventilation. It's best to attack the problem as hypoxia first by going on oxygen. After doing this, you should check to see if the regulator has been functioning properly. Then, you should give attention to consciously slowing the breathing rate. CO. Carbon monoxide, CO, is a colorless, odorless, tasteless gas. It has a much stronger affinity than oxygen for hemoglobin, the substance in your blood which normally transports oxygen. If a hemoglobin molecule is occupied with a CO molecule, oxygen can't get aboard and be transported. Good night, Irene. CO poisoning is cumulative and dangerous. It can incapacitate quickly and is rapidly fatal. Because of the already reduced oxygen supply at higher altitudes, you're even more vulnerable to the effects of CO poisoning as you head upward. Carbon monoxide is a byproduct of combustion. Every winter, people across the country lose their lives when they burn charcoal or other substances indoors for heat without adequate ventilation. For pilots, the danger arises from exhaust gases leaking into the cockpit. This can occur because of a leak in the exhaust system or because there is a leak in the heater, which uses exhaust gases to warm air that is sent to the cockpit. Heaters normally work by passing outside air over the heater's manifold, then directing the air into the cabin. If a leak occurs, raw exhaust can be imported directly into the cabin. If you notice the odor of exhaust or experience symptoms of headache, drowsiness, dizziness, or loss of muscular power when the aircraft heater is in use, immediately turn off the heater if it is in use and open the air vents. Consider opening the windows if that can be done in flight in your aircraft. Consult the pilot's operating handbook. The smell of exhaust gas should be considered the prelude to an emergency. You must act immediately. If your physical symptoms are severe or continue after landing, you should seek medical treatment. Ear ye, ear ye. The bane of many pilots is a tiny, flaccid tube which connects the middle ear to the back of the throat. It's normally closed. In an ascent, the eustachian tube opens for a second or two, permitting higher pressure air from the middle ear to flow out, equalizing the pressure inside the ear with that of the cabin. See Figure 2. This process, often accompanied by slight crackling, is rarely a problem. On the way down, however, things get tougher. Now there is high pressure on the outside and low pressure trapped in the middle ear. The collapsed eustachian tube is like a hose with a crimp in it, and it doesn't open as readily as it did when you were upward bound. You are now in the position of trying to force water back into the hose. Any nasal congestion will make the problem a lot worse, since it puts additional pressure on the collapsed tube, making it even more difficult to get it open. If you can't get the tube open, you have what's known as an ear block. Contrary to the belief of some pilots, this is not a hit in the head from an NFL lineman, though if you ever get an ear block, you may well feel like you've got an entire football in your ear. If you don't equalize the pressure, the results will be somewhere between excruciating and devastating. As the pressure differential builds, your eardrum bows inward, pressing on sensitive nerves. If the pressure differential is too great, the eardrum ruptures. This is not generally considered to be fun by any but the most bizarre of pilots. The first line of defense against ear block is to stop descending and even to climb back up to a higher altitude. The lower you go, the greater the pressure differential, and the less likely you will be successful at springing that trapdoor open. The second thing to do is to swallow, yawn, or tense the muscles in your throat. What you're trying to do is straighten the eustachian tube out a bit and give it the best chance of opening and equalizing the pressure. When this happens, it's generally accompanied by a loud popping sound and an enormous sense of relief. No go? Okay, time for the heavy artillery. What virtually every pilot and flight instructor will tell you to do is perform the Valsalva maneuver, in which you close your mouth, pinch your nose, and breathe out in short puffs against the closed nostrils. I don't recommend you do it. The Valsalva maneuver is potentially damaging, and it's unfortunate that it has been so blithely handed down as the way to clear a closed eustachian tube. Even airline flight attendants will tell passengers to perform the Valsalva maneuver. What's the right answer? Though almost nobody has heard of it, the Toynbee maneuver is a far preferable way of opening the eustachian tube. Tell a friend. Do not fly with a cold or other upper respiratory infection, even a little one. The bad news is that I know you will eventually ignore this advice. The good news is that I know you will probably only ignore it once, because the resulting air block will be a very memorable experience. An upper respiratory infection is like standing on the garden hose. The water just doesn't have much of a chance of getting through. When it comes to your ears, there is no such thing as a minor cold. The least bit of fluid and gunk in your head will compress the eustachian tube and make equalizing the pressure on descent almost impossible. Now that you know better, share the information with your passengers. Don't subject them to the pain and possible injury of an air block. If you do land with an air block and it doesn't clear shortly after landing, give your doctor a call. On several occasions, one concerning me, another concerning a passenger, I had to climb back up to altitude to reduce the pain of air block. A more gradual descent eventually helped relieve the pain. Spatial disorientation. During visual flight, our sense of sight determines the relationship between aircraft attitude and the Earth's surface. When flying in the clouds, though, we control the airplane solely by reference to the instruments. Deprived of the normal visual cues, the body can send some very unusual messages to the brain, creating a profound conflict between what the seat of your pants is telling you and what the instruments say. Such a conflict is known as spatial disorientation or vertigo.
Now, I said you're likely to experience vertigo during instrument training. All private pilot applicants must have some training on flight by instruments, or during day or night flights when the horizon isn't easily defined or identifiable. In such a condition, you might find yourself convinced that you're turning while the instruments are showing straight and level flight. Which do you believe? You must never forget the one most important rule about vertigo. Trust your instruments. I can assure you that regardless of how much experience you have, vertigo can affect any pilot. Pilots experience vertigo should always believe their instruments instead of their bodily sensations.
Vertigo is caused by problems associated with three of our sensory systems: vestibular, kinesthetic, and visual. The visual system is exactly what it sounds like: information sent to our brain from our eyes. The kinesthetic system is the sensory information sent to the brain by the seat of our pants. It's the information transmitted by sensors in our skin and from areas deeper within our body. You don't have to be a rocket scientist to understand how both of these systems work. The vestibular system, however, does require a little explanation. The vestibular system consists of the semicircular canals located in the inner ear, Figure 3. These canals consist of three circular tubes, each containing a fluid, whose movement causes the bending of small hair filaments known as otolith organs, located at the base of each canal, Figure 4. Movement of the fluid within the tubes, caused by acceleration, a change in direction or velocity, stimulates the otolith organs, alerting the brain that the body is in motion. Notice that all three tubes in Figure 3 seem to lie in three planes, corresponding somewhat to the three axes of the aeroplane. This alignment allows you to sense angular acceleration in any one of these planes. In other words, you can sense yaw, roll, and pitch. When you move your head or accelerate the aeroplane, change speed or direction, fluid within these canals move as shown in Figure 4, position B. Since the fluid within the canals has a small amount of inertia, a tendency to resist change in motion, it tends to remain stationary for a short period of time before moving. Thus, the canals can be said to rotate around the fluid within them. Eventually, the fluid catches up to the movement of the canal and the feeling of turning stops, position C. Even though you're still turning, you don't feel it. When you stop turning, however, the fluid continues its motion for a short period of time because of its inertia, position D. This signals your mind that you've entered a turn in the opposite direction. The semicircular canal system was designed as a ground-based system where gravity always pulled the body in one direction, straight downward. In flight, however, gravity is not the only force pulling on the body. Centrifugal force as well as gravity tugs on the seat of the pilot's pants, as shown in Figure 5. This explains why your eyes may tell you one thing when looking at the instruments, while your brain and your body tell you something entirely different. For instance, when the body is in a prolonged turn, the fluid in the canals eventually comes up to speed with the canal walls, hair no longer stimulated. If the head is then tipped or twisted, the fluid once again moves relative to the canal walls. Now a new sensation of rotation occurs based on which way the head was turned, even though the airplane didn't change its attitude. Thus, abrupt head movements under instrument or instrument-like conditions can cause you to perceive maneuvers that aren't really happening. This vertigo-type illusion is called the Coriolis illusion. If you try to correct or turn your airplane in compensation for the sensation, you could be in for a real surprise. Now you know why it's best to believe your instruments. When you start work on your instrument rating, which I hope you will do this someday, you'll learn all about detecting if and when your instruments are lying to you. Right now, it's best to believe them and avoid instrument or instrument-like conditions. Visual illusions. There are situations where, as a VFR pilot, you can encounter instrument-like conditions without being in a cloud. At night, a blending of the earth and sky is often responsible for creating an indiscernible horizon, which is an instrument-like condition. This is most prevalent on moonless nights where stars take on the appearance of city lights and city lights appear to be stars. Figure 6a. Another common visual illusion occurs when you are flying in the direction of a lit shoreline. With dark water underneath, it's easy for shoreline lights to be mistaken for stars, as shown in Figure 6b.
Flying above a cloud deck can produce an illusion of a false horizon. If the cloud tops are sloped, you may find yourself attempting to align the aircraft with the horizon made by the clouds. Flying towards the sun on a hazy day can eliminate the horizon, making it difficult to tell which way is up or down. Situations like these are best handled by climbing above the haze if possible, or getting closer to the surface to establish visual ground contact.
You should be cautious and avoid flying in inclement weather conditions. It's quite easy to lose reference when clouds or other obscuring phenomena are present. Problems with spatial disorientation occur when pilots no longer have sight of the horizon. Unless you're instrument rated, avoid flight anywhere at any time where you might lose visual references. Flight vision. Make no mistake about it, vision is your most important sense. There is no such thing as a medical waiver for pilots without vision in both eyes. Your vision is important for many reasons. First, you obviously need it to fly the aeroplane. You also need it to read charts, look for traffic, and scan instruments. Let's learn a little about how the eye functions. Your eye. Figure 7 shows a side view of the human eye. Light passes through the pupil and lens, then falls upon the retina at the very back of the eye. Light-sensitive cells of the retina are made up of individual cells known as rods and cones. Cone cells. Cone cells are concentrated in a small section of the center of the retina known as the fovea. These cells decrease in number with distance from the center point. While the eye can observe an approximate 200-degree arc at a glance, only the light falling on the fovea has the ability to send the brain a sharp, clearly focused image. All light falling outside the fovea will be of less detail. Figure 8. For example, an aeroplane at a distance of 7 miles, which appears in sharp focus within the foveal center of vision, would have to be as close as 7/10 of a mile in order to be recognized if it were outside the foveal field of vision. Cone cells are responsible for allowing you to perceive color. Looking directly at an object, most of the image is focused on the fovea. Unfortunately, the cones don't work well when it's dark. This explains why it's difficult to perceive color at night compared to the daylight hours. Rod cells. No, they didn't name them after me. Rod cells, concentrated on the outside of the fovea, are dim light receptors. Since these rods are located outside the fovea, they are responsible for our peripheral vision, as shown in Figure 9. Moving images are more easily detected by rod cells than by cone cells. Catching an object out of the corner of your eye is an example of rod cells at work. As I've already mentioned, cone cells don't work well in the dark, which explains why it's difficult to see an object at night even though you're looking directly at it. This is why we have a night blind spot in the center of our vision, where the light from a dimly lit object falls directly onto the fovea. Figure 9.
If you want the best view of a dimly lit object, you need to expose the rods to the light. You can do this by using your peripheral vision for off-center viewing. Simply look 5 to 10 degrees to the side from the center of the object you want to view. This allows some of the object's reflected light to fall on the rods. You can demonstrate this process at night by looking directly at an airplane strobe light head-on and offset a few degrees. A direct view dims the object, while an indirect view increases its brightness. Think of looking at a dim object at night as you might think about looking at a carnival worker. In other words, try not to look directly at their tattoos for fear of finding misspelled words.
Night vision. How well you see at night is determined by the amount of light passing through the pupil. Pupils close to prevent the eyes from receiving too much light and open when light intensity diminishes. The problem is that it may take at least 30 minutes for your eyes to completely adapt to the dark. You can, however, achieve a moderate degree of dark adaptation within 20 minutes under dim red cockpit lighting. This is one reason why you want to avoid very bright lights for at least 30 minutes before the flight if you're planning on flying at night. If you must use a bright white light in the cockpit at night, try closing one eye while the light's in use. This keeps the other eye night adapted. Be cautious. This looks like a wink and one of the passengers may think you're trying to put the make on them. Using sunglasses for protection from glare is most helpful in preventing night vision deterioration, as well as preventing eye strain and eye damage. Find sunglasses that absorb at least 85% of the visible light, 15% transmittance, and have minimal color distortion. Usually a green or neutral gray is a satisfactory color. I'd recommend that you stay away from sunglass frames like Elton John wears. Personally, flaming pink flamingo glasses don't do much for me at all, and I can hardly see how they would help you during your private pilot check ride. I make it a point to ensure all my sunglasses have a high degree of impact resistance. Why? They are excellent eye protectors in the event that something penetrates the windshield. Haze and collision avoidance. Keep in mind that all objects, traffic included, appear to be farther away in hazy conditions. The mind equates difficulty in seeing an object with increased distance. As a result, you might allow another airplane to get closer to you under hazy conditions before taking corrective action. Wearing yellow lens sunglasses is often recommended for hazy, smoggy conditions. Yellow lenses allow for greater definition and contrast of objects. I keep a pair in my flight case for hazy days. I also have a pink-rimmed pair in case I meet Elton John at the airport. Yellow lens sunglasses put a little more strain on my eyes if I wear them for a long time, but the payoff is in easier identification of traffic in smoggy and hazy conditions. Scanning for traffic during the day. Avoiding mid-airs is predicated upon one important premise: you must look outside the cockpit. Far too often, pilots spend their time with their head inside the cockpit staring at instruments instead of honoring the see and avoid concept. How much time should be spent looking outside and inside the cockpit? Many years ago, a military study indicated that on a 17-second cycle, approximately 3 seconds should be spent inside the cockpit, with 14 seconds spent looking outside. That's approximately a 1 second inside to 5 second outside ratio. These are good numbers to follow.
Looking outside the cockpit is one thing. Knowing how to look, another. Scanning for traffic requires that you understand another peculiarity about the eye. Objects are difficult to detect when the eye is in motion. Effective scanning requires the eyes be held still for a very short time to detect objects. Perhaps the best way to scan is to move your eyes in a series of short, regular spaced movements that bring successive areas of the sky into the central visual field. The FAA suggests that each movement should not exceed 10 degrees, with each area being observed for at least 1 second to enable detection, as shown in Figure 10. Since the brain is already trained to process sight information presented from left to right, you will probably find it easier to start your scan over your left shoulder, proceeding to the right across the windshield, as shown in Figure 11.
Whatever you do, don't forget to scan the area behind you. Many years ago, an AOPA, Aircraft Owners and Pilots Association, study indicated that the majority of mid-airs occur with one aircraft overtaking another. One study indicated that 82% of the accidents occurred this way. Obviously, this is a faster aircraft overtaking a slower one. This becomes a greater concern when you're operating in an area where fast and slow aircraft mix. Scanning the rear quadrants may take some neck bending, or turning of the aircraft, depending on the aircraft configuration. Granted, unless you've seen the movie The Exorcist, you may not realize that such neck twisting is possible. Nevertheless, even if your head can't spin on its axis, make gentle turns in the airplane to take a peek at what's behind you. Figure 12. Making gentle turns is also a good idea when climbing or descending on an airway to check for traffic.
Another consideration when scanning is to prevent being a victim of empty field myopia. This condition usually occurs when you're flying above a cloud or haze layer with nothing specific to focus on outside the airplane. This causes the eyes to relax and seek a comfortable focal distance ranging anywhere from 10 to 30 feet. This means you may be looking outside the airplane without actually being able to identify traffic. To overcome this problem, you should try to momentarily fix your eyes on a ground object off in the distance, if possible, before commencing your scan.
If you spot a target and it has no apparent motion, then it means one of two things. It's either coming directly at you or moving away from you, or a big bug has smashed into your window. Targets moving directly toward you can close the distance in a very short time. Figure 13 demonstrates how quickly aircraft can converge. Little or no relative movement can also occur when aircraft are converging, as shown in Figure 14. If you detect a target with little or no relative motion in your windshield, it's best to take evasive action immediately. Don't just wait for the target to grow larger. Make a turn. Make the target move. Just remember to scan the entire area for collision avoidance prior to starting any maneuver. Also, remember to raise the inside wing of a high-wing airplane and look before beginning the turn. If you're flying a low-wing airplane, don't forget to look in the direction opposite that which you'll turn. Why? The outside wing will often prevent you from seeing any converging traffic. In short, do what your mom told you to do. Look both ways, then look up, down, behind, and ahead. Keep your head outside the cockpit. No, that will mess up your hair. I mean keep your eyes outside the cockpit. Night scanning for traffic. While it's easier to spot aircraft lights at night, this doesn't necessarily mean it's easier to identify the aircraft's direction of movement, much less its size and shape. That's why airplanes are required to have their position lights on from sunset to sunrise. Anti-collision lights are to be on when the airplane is in operation. You can determine the direction of airplane travel by noting the position of the airplane's red navigation light on the left wing, the green navigation light on the right wing, and the steady white light on the tail. The red or white anti-collision light is often visible from many directions. Figure 15. One more thing before we leave the topic of night scanning. Something known as autokinesis, meaning self-moving, might occur at night if you don't keep up a regular scan pattern. Staring at a single light source for a few seconds at night can cause that light to appear to move, much like an aeroplane on a collision course. If you're using the light as an attitude reference, this apparent motion could cause you to lose your spatial orientation. You can prevent autokinesis by scanning in the manner I've previously discussed, as well as by observing the flight instruments to affirm the correct attitude. Aeroplane blind spots. All aeroplanes have blind spots where traffic is difficult to see. High-wing aircraft make seeing above difficult, while low-wing aircraft make seeing below difficult. Biplane pilots have both problems. Figure 16 shows how these blind spots look on different aircraft. This doesn't mean that it's impossible to see in the directions of blind spots. You may need to turn the airplane or lift a wing to compensate for those areas blocked by aircraft structure. This is one reason I recommend that pilots of high-wing airplanes lift their wings slightly and look before starting a turn. Tell the passengers that you're looking for traffic if you're worried that they may think you don't know which way to turn. This prevents turning into an airplane that is descending from your direction of turn. Pilots of low-wing airplanes need to be especially alert to clear the areas below them during descents. If you're flying a low-wing airplane, be sure to make the necessary clearing turns during descents to check for traffic below you. Whatever you do, don't be hesitant to turn that airplane and look when operating in areas of high traffic density. It's possible for a low-wing and a high-wing airplane to remain within each other's blind spot as shown in Figure 17. This isn't how they make biplanes either. This is good motivation to keep your eyes open and the airplane maneuvering to clear those blind spots.
Hello, Americans. Page 3. If there is ever a good time to remain vigilant for traffic, it's when you're within 5 miles of an airport below 3,000 feet AGL. One study of mid-air collisions found that 77% of all mid-airs occurred within these distances. That same study reported that 49% occurred within 5 miles and 500 feet AGL of the airport. This translates into a need to be careful when you're approaching an airport to land.
Don't let the presence of a tower controller relax your vigilance. Many a mid-air has occurred in the presence of a tower-controlled field. Pilots are still responsible for their own see and avoid traffic separation even when the tower is in operation. Filing a VFR flight plan. Although not required, it's simply good practice to file a VFR flight plan for all your cross-country trips. A VFR flight plan filed with the nearest flight service station is good insurance in case your airplane is forced down for any number of reasons, including bad weather or engine problems. Since every flight plan has a departure time and an estimated time en route, ETE, an FSS specialist will be expecting you to close that flight plan when the ETE has expired. After 30 minutes or so past the estimated time of arrival, search and rescue procedures are initiated. This usually starts with a ramp search of the destination airport and can end in a full-scale search and rescue operation by local authorities. Fortunately, most airplanes are found on the ramp at the destination airport because the pilot forgot to close his or her flight plan. You can close it with the nearest flight service station by phone or radio. Let's examine how to file one of these flight plans. Figure 18 shows a typical flight plan form. Block 1. Check the type of flight plan you're filing. In this instance, you'll be filing a VFR flight plan. Block 2. Enter your complete aircraft identification including the N prefix if you're flying a U.S. registered aircraft. Block 3. Enter the designator for the aircraft followed by a slant and the transponder or DME equipment code letter. This code tells ATC about some of the transponder and navigation equipment on board your airplane. The following are the typical codes you might use. Slant X, referred to as slant X-ray, no transponder. Slant T, referred to as slant Tango, transponder with no altitude encoding capability. Slant U, referred to as slant uniform, transponder with altitude encoding capability. Slant D, referred to as slant delta, DME but no transponder. Slant B, referred to as slant bravo, DME and transponder but no altitude encoding capability. And slant A, referred to as slant alpha, DME and transponder with altitude encoding capability. If you're flying a Cessna 152 with DME and a transponder with altitude encoding capability, you would write C-152 slant alpha in Block 3. In the unlikely event your airplane went down, it's possible that ATC might be able to retrace your flight path based on their radar tapes if they know the equipment signature of your airplane. For instance, if your airplane has a transponder without an encoding altimeter, they could discount all airplanes appearing with an altitude readout. Block 4. Enter the true airspeed you've computed based on your altitude and performance chart information. Block 5. Enter the departure airport identifier or the name of the airport if the identifier is unknown. United States airports have 3 or 4 letter or number identifiers. Looking on the sectional chart next to the airport name, you may find the airport identifier in parentheses as shown in Figure 19. Block 6. Enter your proposed departure time in Coordinated Universal Time, UTC. If you are airborne and are filing the flight plan with the FSS, specify the actual or proposed time you'd like the flight plan activated. Keep in mind that the VFR flight plan is held by the flight service station for 1 hour after the proposed departure time. Then it's eliminated from the computer if it hasn't been activated. If you're running late and have filed a flight plan, call the flight service station and give them a revised proposed departure time. Block 7. Enter the VFR cruising altitude at which you intend to fly. If you're planning on using more than one cruising altitude, list the first one you intend to use. Block 8. Define your route by NavAid identifiers, such as 3-letter identifiers for VORs or NDBs, or names if you don't know the 3-letter identifiers. Airways or waypoints if you're using RNAV. For instance, I could depict my route as SLI, POM, V197, EHF, V165, PTV. This tells the flight service station specialist that I'll fly from my departure airport, don't need to list the departure airport in the route since it's already listed in Block 5, to the SLI VOR, direct to the POM VOR, then via Victor 197, an airway, to the EHF VOR, then via Victor 165, also an airway, to the PTV VOR. I don't need to list my destination airport in the route section since it will be listed in Block 9. If you plan on stopping at different airports en route, simply list them in the Remarks section, Block 11. For instance, With the routing listed above and with a final destination of Porterville, I might elect to stop at Brackett Field to stock up on pilot supplies and Rosamond for lunch. In the remarks section, I'd list intermediate stops at Brackett and Rosamond. I could, of course, file 3 separate flight plans for each stop, but this is more work.
Now folks, we're coming into Block 9 now. Now listen up. Enter the destination airport identifier code as you did with the departure airport. You can elect to file something unofficially known as a round-robin flight plan. Suppose you wanted your flight plan to reflect a flight to an airport with a return to the original airport of departure. And in this instance, you'd simply list the departure airport in the destination airport Block 9. The route listed in Block 8 would be to the first airport and then reverse back to the departure airport. In the remarks section of the flight plan, you can put the words round robin if you like. This signals the flight service station specialist of your intention, although it's not necessary to list this since the destination is self-explanatory. If you plan on making 1 or more stops along the way, it's recommended that a separate flight plan be filed for each leg when the stop is expected to be longer than 1 hour.
Block 10. Enter your estimated time en route based on the latest forecast winds. Give yourself a little time cushion, if necessary, so you don't need to rush to close a flight plan. While en route, if you find that you're running late, simply call the nearest flight service station and ask them to extend your flight plan. Remember, when the ETE is up, based on the actual time you opened your flight plan with the flight service station, you're technically overdue. That doesn't mean that the flight service station personnel are going to drop everything and start looking for you immediately. After a short grace period, usually 30 minutes, they'll make a call to the phone number listed in Block 14. If they can't find you at home, they'll start a ramp search, then launch into a full-scale search and rescue operation. That's why you want to close your flight plan as soon as possible after you land. Block 11. Enter the remarks you feel are important. Try to keep them as short as possible simply for clarity and ease of reading. You'll probably hear IFR pilots say that the remarks shouldn't be longer than 15 letters. While that's true for IFR pilots, it's not true for VFR pilots. If necessary, write whatever will fit into the block. Your flight plan is kept on file at the flight service station at which it is filed. In the event search and rescue is necessary, the original flight plan is referred to, along with your original remarks. For instance, if your flight is over water, you may mention that you have flotation equipment, signaling devices, and portable ELT. Write anything that might be useful to someone looking for you in the rare event of an emergency. Block 12. Enter the amount of usable fuel on board, computed from the departure point and expressed in hours and minutes. Block 13. Enter an alternate airport that you might land at in the event the destination airport becomes unavailable for whatever reasons, such as runway closure, bad weather, etc. An alternate airport isn't required for a VFR flight plan. You can choose to leave this block blank. Block 14. Enter the complete name, address, and telephone number of the pilot in command. Block 15. Enter the number of people on board the aircraft. Block 16. Enter the predominant colors of the aircraft. This information is especially important for search and rescue. You can file the flight plan by writing it out on paper and handing it to the flight service station specialist or via DUATS, the Computer, Flight Plan, and Weather Service, or via a service known as File. You can access FastFile by calling 1-800-WX-BRIEF, that's 1-800-WX-BRIEF, and listening for the appropriate keypad inputs. A recording starts and you simply read your flight plan into the phone. It will be put into the flight service station computer a short time later by an FSS specialist. When airborne, you open your flight plan by calling the nearest flight service station on the radio. If the departure airport has a tower and they aren't too busy, you can ask them to open your VFR flight plan. They simply make the call to the flight service station for you. The moment you open the flight plan, the time starts counting down from your estimated time en route. This is why you always want to note this time and, as I've already mentioned, be prepared to extend the time with the nearest flight service station if you're running late. Keep in mind that the tower doesn't automatically close your VFR flight plan upon landing, assuming you landed at a tower-controlled field. If you ask them to, and they agree, then you can assume the flight plan will be closed.